let's remember what we talked about earlier, right? We did sampling distributions. Can anyone remind me what, or in their own words, roughly what's a sampling distribution? So we take a sample from the population, okay? Yeah. So, right, what we talked about, right, is you have these samples, right? You take a mean from each of it. That mean won't always be the population mean. Most of the time it won't be, right? But you can make a histogram of those plots, right? And as you were saying, the mean of that sample mean, the mean of all the sample means should be equal to the population mean. There are some other things that happened though. So the means didn't change, right? That which makes sense. What did change about like the shape? So the larger the size of your sample is, what happened to the shape of the distribution? Becomes more normal, right? That's one thing that it does. Becomes more normal. What also happens to the spread of the distribution? Becomes narrower, right? Sorry about this. Forgot what's going on there, right? Okay. It becomes narrower, right? Which means what measurement? So the spread decreases, right? So the sampling distribution is going to always have a smaller, what's the main thing we use to measure the spread? Say again? The z-score tells me where one standard deviation, right? So the z-score tells me my relative position, right? Your z-score would tell, like for your height, would tell you how your height compares to the other members of the population, right? But it does not tell you how spread out that population is, right? Because it's a measurement for you. So remember, right, spread, right, like we can use range, but that's not a great measurement because, right, that's very affected by the outlier. So what happens, right, is when you do the sampling distribution, right, I'll give you some symbols, right? So the mean of the population, I'm going to use this. So this means mean of X bars. So that means the mean of means. That's the same thing, right? But the sampling distribution, right, this becomes normal-ish, right? And, well, what happens to the standard deviation? This is the standard deviations, right? It's significantly smaller, right, than the standard deviation of the population, right? And this becomes even smaller, right? Sorry, I didn't write, as n increases. Okay, but we only got a qualitative sense, right? We didn't say how much smaller. We didn't say how normal, if that even makes sense, but you kind of get what I'm saying, right? Like a uniform distribution is not normal at all, right? Something that looks maybe, right, like it was kind of, some of the distributions were jagged. They weren't completely normal, right? So we're going to talk about all of that in this section here, right? So this is the central limit theorem, right? And to do that, you have to understand the sampling distribution. So it's good that we talked about that. So we're going to calculate the sample, the mean of the, so this, maybe I wrote this in a way that, we're going to calculate the mean of the sampling distribution, which we already know it's the same thing as the mean of the population, right? We know that the standard deviation is not the same, it's smaller, right? But how much smaller, right? We're going to tell you about that. You need to be able to, right, explain the central limit theorem, right? Before, right, if I told you, like, if I gave you the appropriate information, right, aka mean and standard deviation, I could say, hey, what's the probability that someone's height is between, let's see, 72 inches, that's 6 feet tall, right? And let's say 70 inches, 5'10", right? Since height is normally distributed, you could convert these both to z-scores, right? And you could figure out this probability if you had the appropriate numbers involved there. What you're going to be able to learn to calculate now, right, is a little bit different. You're going to be able to calculate what's the probability that the mean of a sample size, and I'll have to tell you is between 70 and 72, right? Now, which one of these is going to be a smaller probability? Well, actually, I didn't tell you what the X bar is, right? But it's less likely that your sample mean will vary from the population mean less than an individual member, right? So like, yeah, we'll kind of figure that out, right? Because that standard deviation gets narrower, right? So if you average over a large number of people, that's less likely. You're less likely to get an extreme group of individuals, right, than to have one member be extreme in some manner. Okay, so you didn't need to follow all this. I'm just kind of giving you the different things that you need to be able to know how to do. Okay. So the central limit theorem, one is nice because we don't always know, like in these problems that I'm giving you, right? I always say the distribution is normally distributed, right? And then you can tell me certain things with z-scores, right? You can give me a probability if I give you z-score. Does that sound familiar? That's what we did in all of the previous sections in chapter 6, yes? But let's think of you're studying something ahead of time, right? And there are other sections of the book that cover this better, right? If you're studying something that hasn't really been studied, right? Let's say I'm interested in the distribution of wing size on grasshoppers. I don't know how I came up with that, right? But, right, ahead of time, right, if I asked you, Bobby, do you think that that's normally distributed? You would say, well, you have no idea, right? So that's one problem, right? So, but the central limit theorem says that your sample, remember we did this, right? That dice roll, when we rolled those dice, that was a uniform distribution, right? When we rolled the dice, you were as likely to get a 6 as you were to get a 7, or not a 7. That's not something you can roll on a dice, right? As a 5, as a 3, right? But when you made that sampling distribution, you were much more likely to get means that were closer to 3.5, right? Does that sound familiar? So, yeah, and so it became normal, right? But as we said, right, I forgot who said, but Mons, was that you said that it becomes more normal? Right. So the question is, how normal is normal enough that we can treat it as if it's a normal distribution, right? So that's the first thing I'm going to tell you, right? This is a key concept, right? So as n increases, right, it becomes more normal. And I don't know, someone who's, right, like my coursework in my master's degree was not like statistically focused. I definitely know enough to teach this class, but some things I'm not entirely sure. I don't know why n equals 30 was decided, right? But notice it's greater than 30. So if you have a sample size with where n is greater than 30, the sampling distribution can be approximated by normal distribution without significant errors. So what that means is if n is greater than 30, it's normal enough to say it's normal. It's not completely normal, right? Really, it only becomes normal if n is infinity, which obviously you'll never have, right? But we could say it's normal enough. Now, it doesn't say this in this slide. We'll say it later. The other thing is if you know that your original distribution is normal, right? If your original distribution is normal, you're sampling, right? Sampling, the process of doing a sampling distribution makes your original distribution more normal, right? If your initial distribution is normal, it can't be made any more normal. It just stays normal. So then you don't need to worry about the sample size, right? If it's already normal, we know it's normal. Otherwise, we know by the central limit theorem, hey, if n is greater than 30, right, we can assume it's normal. Now, if n is 10, it's more normal than if n is 5, but 30 is where we're going to say that's the limit, right? So it's a normal distribution, right? But a normal distribution, every normal distribution has a mean and a standard deviation you need to know, right? Now, Regina reminded us that the mean of the sampling distribution is the same thing as the mean of the population. So so that's why it says with mean mu, because mu is the population mean. So we stick with a mean of yes. But we said, right, who pointed out, someone mentioned that it got narrower, right? Right, that was, yeah, Moss, right? So how much narrower? This is how much, right? So your new standard deviation is your old standard deviation divided by, does everyone know this symbol, square root symbol? Right, so this is the number when you multiply it by, so like square root of 16 is 4 because 4 times 4, right? So the new standard deviation is smaller, right? So this is why it's better to collect a large sample, right? So the new standard deviation is the old standard deviation divided by square root of n. I'm going to move on to the next slide, but it's going to be have the same pieces of information, all right? Don't worry. So this is basically just saying this in math, right? So the new thing, so this subscript, right, with x with a hat. X with a hat means the sample mean, right? So this means the population mean of the sample means. We've talked about this before, right? This is weird. This is the population mean of the sample means is equal to the population mean, right? That's just what Regina was saying, right? We don't have to worry about changing the mean, right? As Mon said, as we all saw, right, those sampling distributions, it's just weird.
And then they can also be playing your schedule around like.
None of my other classes ever have a tour walk by them, so this is just I guess they do tours during this class, and they always walk by that exact spot. It's kind of funny. All right. So that's what this is saying. So these symbols, it was a little confusing because we didn't have the symbol before on the previous slide. So this is saying the new standard deviation, right, of your sampling distribution is equal to your old standard deviation, the one of the population, divided by the square root of that sample size. And this formula gives you the how you use z, right, for when you're talking sampling distribution. Now, I wouldn't write it this way because it's confusing as the complex fraction. I would just remember that I would calculate my mu x, my sigma x first. Just remember, I'm looking at mu of x bar, or sorry, sigma of x bar. So notice this is different. Our old formula for z was this. Notice in the old formula, there's no x bar in it. It's x, right? Because before, right, if I want to know what's Bobby's z-score, right, that's how do you compare, right? So that's an individual, right? It's a one piece of data, right? I put Bobby's height into that formula. And since he's just one person, right, I would want to use the population standard deviation, right? But here, this reminds you, right, to figure out how unusual, how extreme a sample mean is, I would want to use a sample mean, right? So perhaps I use this class as a sample, right? I take our mean height, I would subtract mu from it, so that part's the same. The only reason why this part's the same is I could say, hey, actually, this is supposed to be mu x hat, right? Or mu x bar. But as Regina pointed out, these two things are the same, right? So we don't need to worry about that. So notice the requirements is that either we know that the original population has a normal distribution, right? Or n is more than 30, right? when we increase that n, our distribution, we take our initial distribution, we kind of normalize it. We make it more normal as n gets bigger and bigger, right? So we know, hey, regardless of your initial distribution, if n is bigger than 30, it is normal enough, right, to treat it as if it's normal. Now, the other way you could know that it's normal is, well, if your original distribution is more normal, can't get more normal, right? Something's neither normal or it's not, right, as far as that goes. So if it's already normal, we know that the sampling distribution will be normal regardless of how big n is. So either one is enough to be able to use this. However, if the original population is not normally distributed, although it's not necessarily not normally distributed, it could also be distribution is unknown, right? And n is less than or equal to 30. It's not, we don't know if it's well enough approximated by a normal distribution. And we just can't necessarily do anything with it. So it's not that there would be some other method you would need to calculate, or it's just like you haven't taken enough data. So this is just requirements to be able to do the stuff that I'm going to teach you how to do later in this class. Questions here? Okay, so basically when considering a problem, so first you need to know, can I even solve this problem? Right? So you'll either need to know that the original distribution is normal or the sample size is over 30 or both, right? That information will be clearly given to you in the problem. Here's the other thing, and this is going to come up next on the celebration. It won't really come up now, though. Is when you read a problem, right? Like, actually, this is not a bad idea. Let's turn to the practice celebration, right? Let's go to the last page. So it says, look at number 5, right? So if you read the last sentence in number 5, it says, what is the probability that 16 randomly selected quarters will have a mean weight of 5.47 grams or higher, right? So that means we are looking at a sampling distribution, right? Now, if you read, let's go to the page before that. Let's actually look at question 4 because it's very similar, right? It says a vending machine will accept coins weighing between 5.25 grams and 5.65 grams, right? Notice there it's talking about an individual coin. Is that coin, what's the probability that that coin is in between those two numbers, right? Here on that, so that's in 4, it's saying a single coin. Here in problem 5, it's saying what's the probability that the mean will be above a value, right? So when you're reading these problems, you need to determine, right, am I using a single value, right? If it's a single value, what you did before, right? It's what we've done in the previous sections in chapter 6. Right? And then notice you can just use the standard deviation. It doesn't need to be changed, right? if you are not talking about a single value, but instead you're looking at the mean of a sample values, right? So we're going to be focusing on doing this number 2 today, right? Because we already focused on doing number 1. But the tricky thing is when you celebrate, you have to be able to distinguish between, is this a question asking me to do a number 1 thing or a number 2 type thing here, right? So big keywords, right? If you're looking at something involving the mean, right? A mean is a keyword that will tell you, right, that you need to change your z-score. And really the only big change, right, is if you have a sample, that means your standard deviation isn't whatever standard deviation is listed there. It's the standard deviation of your population divided by the square root of your sample size. So this is a big mistake that students who make mistakes make, right? It's typically that students just go in thinking it's a single value, right? So that means they don't end up adjusting the standard deviation. So this one's used for samples, right? Mean of a sample. This one would be, what's the probability that this group of 30 people has a mean that's a mean weight over 150 pounds? This would be, what's the probability if I randomly select one person, right? What's the probability that their weight is over 150 pounds? So again, this is just reminding you what each of these things are, right? The mean of the sample means is equal to the mean. The standard deviation of the sample means is not equal to the original standard deviation. You need to divide by the square root of n. All right. Now, this is more of a note. I am not going to assess you on this next piece of information I'm giving. But some of you guys, anyone ever look at like videos that are outside of, use material that's outside of like the textbook and my notes? Some of you might, right? Khan Academy might be an example, right? So they might call this thing that we're calling the sample, the standard deviation of the means, right? The standard deviation of the sampling distribution. They might call this the standard error of the mean, or SEM. I will not call that because I find that term confusing. Because like if you take a higher level statistics class, you'll learn about like error just means how, like error sounds like to normal people, an error isn't just something that happens from statistics, it's someone making a mistake, right? So I find this standard error of the mean a very confusing term for beginning statistics students. So I will never use this. Also, I never was really taught, I've not read this term much myself, so I am not going to use it, right? But I just want you to know that that's what it's called in case you look something up and it starts using this term, right? And you're like, what the hell is that, right? But that's just basically saying this is your new standard deviation. It's the standard deviation, right, of your sampling distribution, right? So that's called your standard error of the mean. I don't like using statistical terms that have the word error in it for beginning statistics class because an error sounds like a mistake, right? It's not a mistake. It's something else, right? It's talking about, it's like the accuracy of a technique, right? Whether it's done correctly or incorrectly. So let's actually use this technique, right? And let's see how things go. So is anyone, I don't know, maybe my wife says I'm too observant. Like I read street signs when I'm going by them that I don't need to, right? Yeah, or not for fun. I just do that, right? Or I think, like recently, I was over spring break, I flew to Atlanta, right? And you know, it was Southwest, so they had you line up, right? And like the gate, it said Atlanta, it said everything except for like on the display, like right over the door, the display that no one would look at because you wouldn't see it unless you're about to go on the plane. It said Houston, right? So I was like, but no one else noticed it other than me. This is kind of my thing, right? So when I'm in an elevator, has anyone ever noticed that it typically has like a plaque, one saying when it was last inspected, right? And then it might say a maximum weight and a maximum number of people. Okay, so let's see if those numbers like correspond in a way that makes sense, right? Okay, so I don't know if this is true, so this is oddly specific example, but here we go. So there's an elevator in the car rental building at the San Francisco International Airport. These elevators, right, flights land at a time. Everyone goes to get their rental car at the same time, right? Then maybe no one comes for the next hour. So those elevators are busy. So they might actually get close, right? I've been at the airport where I've had to get on the next elevator because it was too full, right? I'm sure you've all had this experience. So it says the maximum capacity of this elevator is 4,000 pounds or 27 passengers, right? So there's a way that you can read that, right? Let's say that you have 27 passengers on that, right? It is assuming that if you have 27 passengers, it will be less than 4,000 pounds. So if 27 passengers weigh less than 4,000 pounds, right? Divide that 4,000 by 27, you get 148 pounds. Is everyone following me so far? So if you have 27 people on there, if your mean weight is under 148, you're under 4,000, which is cool. If your mean weight is above it, you would have above 4,000. So let's do two calculations, right? So, right, men on average weigh more than women. So worst case, right, as far as elevator weight, let's assume that there are 27 men on the elevator, right? So let's do this, right? So, and we know, right, it tells us here, right? So adult males have weights that are normally distributed with a mean of 189 pounds, a little heavier than I would think, right? And the standard deviation of 39 pounds. That kind of makes sense. That's a pretty hot, big standard deviation, right? So, but people like really weigh, like, it's not crazy to find someone that weighs twice as much as someone else, right? Find someone that's twice as tall as someone else, that's much less likely. So that's a small standard deviation. So let's write these numbers down. So our mean (189), our standard deviation this is already worrisome to me because this converts to a passenger weight that's much less than the mean male, right? But let's actually do the numbers. We already know that this is either like that sign's dangerous or the elevator can hold a lot more than 4,000 pounds, but we'll see that accurately here. So it says find the probability, right? And this is what I was talking about earlier. You have to think about what are you doing. So we want to find out the probability that a randomly selected adult male, right, this is A, has a weight greater than 148 pounds. Okay, so my question here is, are we talking about an individual or are we talking about the mean of a sample? For question A, everybody. An individual, right? So we should use the techniques from the previous parts of this chapter, right? Because this thing on the central limit theorem talks about what happens as you have these sampling distributions, right? A sampling distribution is always like the sample of means from different groups, right? That's not what's going on here. Does everyone follow what I'm saying? No, you don't use the central limit theorem, because the central limit theorem talks about the distribution of sample means. There is no sample, right? It's just one person. So we are trying to find, right, the probability, and then should I write x hat, x bar, sorry, or just x? Considering it's an individual, it is, no, it's an individual. So is it the sample mean, or are we talking about an individual measurement? So that is just x, right? We want to find out the probability that x is greater than no, it just literally, you just literally have to translate what it says there. We're following, I have to find out the probability that x, I'm doing part A right now. Okay. And notice we know that our initial distribution, right, our distribution of adult weight, of male adult weights is normally distributed. So, and it's normally distributed with a particular mean and a particular standard deviation. So solving A, you could have done before today. Hoping, I see a lot of like people paying attention to other things right now. I mean, you're adults, so that's fine, but like, just make good decisions, okay? So how do I do this? We did this before many times in your homework and in the exit ticket. So how do I find, so what do I have to do with that 148? Should be second nature by now. How do I solve this? We got all day. The homework assignment where you do this over and over again, I believe is due today. Anyone done the homework? Any of it? A week ago, I think we probably solved like 5 problems like this. A little long, and we did an exit ticket on it too. I guess I gave you until tomorrow. See, this is the problem. All right, I give you guys a while, but only 6 of 17 of you have started the assignment that's due tomorrow. And it's okay. I give you that flexibility, but I'm just pointing out that we do build on concepts, right? We build on what we do on Monday, right, on the next day of class. So if you haven't started the assignment and you've forgotten what we've done, it gets tricky, right? We're trying to model something here. I do. No, I do something with the standard deviation. There's a formula I need to calculate. Yep. That's absolutely right. So first I need to, so basically what you're saying, Mars, is I need to calculate a z-score that corresponds to this value of x. Does this sound familiar, guys? No, I know, I think that you're not the only one, but why you have to just wait very patiently, okay? You do this, you will get negative, I'm sorry, I kind of didn't fit. That's bad. Negative 1.05, right? That's your z-score, right? So since that corresponds, right? That z corresponds to that x, right? So the probability that x is greater than 148 is the same thing, since it's a normal distribution, as saying what's the probability that z is greater than negative 1.05, right? Because this z and this x correspond to the same weight, right? We did this a lot. So the next step, once you have the z-score, is to draw the picture, right? Okay, so here's my mean, right? Now, since it's been normalized, the middle is 0. So negative 1.05 would be to what side? So that's the left or the right? The left, right? Okay. Now, which side of that line should I be shading? It says, what's the probability that it has a weight greater than 148? To the right. We could use our calculator, or we can use our table. Let's try our table. I find the tables easiest when you have a single z-score. Calculators is easier when you have when you have two z-scores. We have to modify our approach a little bit because what does it say at the top of the table, of your z-table? Right. So, but that's okay. If I find that area, I can easily, my table is actually going to give me my white area, but I can simply subtract that white area from 1, right? So we can say that this thing right here is equal to 1 minus the probability. So you could just do the 1 minus. I'm just writing this out if this doesn't make a ton of. So table gives you the probability that you're less than, right? So you just subtract that probability from 1. So it's 1 minus, and looking at the table, what's the appropriate value? Yeah, so it is, looking at the table, let me just double check. 1.1, so 0.14, 686. Everyone got that? You do this, you get roughly, convert this to a percentage just to make it kind of more concrete to us because we're more accustomed to doing probabilities by percentage. We get 85.3%. Ladies and gentlemen, you may have forgotten how to do, you need to know how to do this. This is like we do a lot more in this chapter than this, but this is the basic skill, right? This is what you go to town on in 6.2, right? And a lot of you haven't started that assignment yet, which is fine. I want to give you time to do it. But like it is ideal that you at least start it significantly ahead of its due date, right? I might have to experiment with giving you a shorter amount of times to do assignments if I don't see that. I know you wouldn't like that, but it might be better for your learning, to be honest. Okay, so this to me intuitively makes sense because 148 is significantly less than the mean, right? Does everyone see that? So, right, 50% of people are greater than the mean. So significantly more than 50% of the people should have weights greater than 148 pounds, right? Because that's a fairly light person, considering that it's significantly less than the average weight. Does everyone follow that intuition? Okay, so we've done A, right? Let's try to guess on B. So B, it says, I have a sample of 27 randomly selected people. Now, people going onto an elevator aren't randomly selected, right? They come off the same plane. Maybe some of them were traveling together. Maybe there's a wrestling convention, so the people there are heavier than average, right? But let's just ignore that for a little bit, right? what's going to happen? Is this going to have a smaller probability or a greater probability? So we want to find that the mean weight of 27 people will be greater than 148. So remember, when this distribution when you do a sample distribution, does it get narrower or wider than the original? Narrower, because the standard deviation decreases, correct? Hmm?
The amount of people,
What do you mean amount of people?
the size of the sample.
The size of the sample increases.
Here's why it goes up. Is that-
What do you mean it decreases? Standard deviation decreases because it is, right? 100, this is a very light person, right? So which is more likely, just intuitively, that you randomly select a person who is very light, or you randomly select 27 people who averaging each other out are very light, right? The second one's less likely. So that means this will be more likely. You'll be more likely to be over this number that is much smaller than the mean. And you'll see that here, right? Just imagine that, right? What's the probability that, you know, the next person you walk into is shorter than 5'1", or what's that probability is a lot higher than the probability that you're going to go into a classroom and that classroom will have an average height of 5'1" or less, right? Just intuitively imagine that. Okay. And we'll see this here. Okay, so now we're doing B. Now, how is B different than A? So in A, we were looking at the probability for the weight of an individual. Here we are looking at the mean of a sample, right? So this one right here, you need to think of this as a sample, right? So before, we were looking at what's the probability. Now the numbers are the same, right? This is a sample, right? And since it's a sample, you need to know the sample size. What's the sample size here, everybody? N equals 27, right? So before, right, we wanted to figure out what's the probability that X was bigger than 148, right? Here, we're trying to figure out the probability that X bar, right? Because we're talking about the mean of 27 randomly sampled individuals, right? But I'm not sure we can actually calculate this. Because what are our requirements, right? To do this, we have to use the normal distribution. And the central limit theorem says, what is the minimum size to be able to assume that it's normal? Yes. 30. What's our sample size here? So does that mean we can use it? The trick here. So it seemed not, because the sample size isn't big enough, but what else? But what do we know about our original sample? It's in a normal distribution already. No, it's a normal distribution because it says adult males have weights, sorry, can't speak today, that are normally distributed. So if it starts out normal, it's going to stay normal, right? So if you know it's a normal distribution, you don't have to work, right? So we're cool, right? It's a requirement. It has to be greater than 30, or the original distribution has to be normal. And that should make sense because you're treating the sampling distribution as if it's normal, right? If your distribution started out normal, it doesn't matter. Like it doesn't matter, right? If your distribution started out not normal or unknown, right? You know it becomes normal enough if your sample size is more than 30. Okay, so notice here we have the mean and the standard deviation for the population, but not from the sampling distribution, right? Well, that's easy. The mean of a sampling distribution, everybody, is equal to what? Regina kept saying this. I wrote it 30 or 40 times on the slide. The mean of a sampling distribution, what is that? It's the mean of the population, right? Which in this case is, sorry, not 148, it's one. I put the wrong number there. Okay. When you use a sampling distribution, the new formula you have is no longer x minus mu, it's x bar minus mu of x bar, the mean of the sampling distribution. Although you don't actually have to write that because we said that they're the same thing, right? But the standard deviation, is that the same? So I said, okay, the mean of my original distribution was 180, right? The mean of my sampling distribution is the same. Can I use the same conclusion? Is this also true? No. What do I have to do? What is the correct formula to use? Let me see. I think I wrote it down about 4 times so far. Correct. So it is our population standard deviation, right? Divided by the sample size, right? The mean of the sample size is less likely to be extreme the larger the sample is, because like if there's an extreme person in the sample, well, it will be averaged into everybody, right? Put this in your calculator, you will get that your sample mean is roughly 7.5 pounds. That's significantly smaller than the of the population, right? Because this is like it's unlikely that all 27 individuals, right, are extreme, right? And they would have to have that low of a mean because, right, if you have like one person in there, their extremeness will be averaged out by everybody else, right? Think about it like that, right? What's more likely that you have an average roll of 6 if I roll the dice 2 times or 300 times, right? Twice, because that's out of the norm. Okay, so then let's calculate our z. So notice to calculate our z, the same thing as before. Step now, we use this small standard deviation. If I do this, not a good time to leave. I get a z-score of negative 0.54, right? And here, right, I am looking for what? So here's my z. I'm looking for area to the left or to the right? To the right. Okay, so we might have to modify because our table. No, it doesn't. So who can help me out what to think of that? You could, but we don't need it. So look at your table, everybody. It doesn't get anywhere close to 5. But let's look at the largest value on our table, which is negative 399. What value does it give you for that? On the negative side, yeah. Tiny, right? Most negative, right? And and it's finding this white area right here, right? And that area is small because I'm very far to the left. I am much further to the left than this thing that gave me this tiny, tiny value, 0.0003. So like 3/100th of 1, no, 3,000ths of 1%. So this area is going to be even smaller than that. So this yellow area de facto is approximately do we get why it's approximately 100%? Because these values, right, we're looking at the area to the right. This table gives us the area to the left, right? If you're off the table, right, you're talking about probabilities that are so low, they're not even worth considering. Yes, you could use the calculator, Mars, but it's not really necessary. Yeah, because the other answer would be like 0.9999999, right? Something that's basically 100%, right? What's the probability that a human being is more than 20 feet tall? You can treat it as if it's 100%, right? Like that's fine, at least for this stuff. And this makes sense to me. So this number is worrisome to me, right? Because it's saying this thing can hold 4,000 pounds, which it's saying is 27 people. But we calculated if all those 27 people are men, the probability that they will weigh together more than 4,000 pounds is basically 100%. So either 27 people shouldn't get on this, or it actually can hold a lot more than 4,000. I don't really want to know. Yeah, that's not even assuming the suit. Yeah, it's ignoring the suitcases here too. Okay, so let me just kind of show you this, and I want you to practice this on your own. I'm going to go around, right? And I'll help you interpret this. So notice this is the individual weights, right, of adult males. It is normally distributed, right? We calculated the probability that a single male will be more than 148 pounds, right? It was 85%, so a large majority, but there are people in here, you know them. My father-in-law is probably in here, right? But what's the probability that 27 males, right? Notice that central limit theorem, right? As that n gets smaller, or sorry, as that n gets larger, you're dividing by the square root of n, right? So that standard deviation gets much smaller, which means that this thing is still normal, right? It's still symmetric and bell-shaped, but it's less out there, right? So notice, just look at the picture. What percentage of the area is to the left of this value? Like nothing, right? So almost all the area is to the right. So let's do some interpretation before I have you guys do one of your own. So they actually calculate it, but this is why I'm saying you don't need to do it. Look at what they found the probability was when they used a more accurate table. 0.999999998. So we got 100%, they got 99.999998. So it's basically the same, right? So there's an 84.5% chance that an individual will weigh more than 148, but the probability that 27 randomly selected individuals on average will weigh more than 148 is much higher. So given that the safe, oh, is this still gonna work? Yeah, the pen's just really crappy now. So given that the safe capacity of the elevator is 4,000 pounds, it will almost certainly be overweight, right? If there are 27 men on it. Okay, so I'm gonna have you do an example, but first I want to introduce this example a little bit, right? So notice that everything we've done in this class so far, and I know guys, I've been talking a long time, I want to give you a chance to work, right, after this. So has been been descriptive statistics, right? You wouldn't actually know a lot of this stuff, right? I'm saying to you, hey, the population mean, that's 100. The standard deviation of the population, that's 10. What's the probability that, hey, if you have a sample of a certain size, the mean will be above 110, right? Sorry. This is weird to me. Does this seem backwards to you of what you would actually know? Let me show you. So I'm telling you, hey, the mean weight of some animal is 100 pounds, right? The population mean. I somehow know the population mean. Is that likely, right? And I somehow know the population standard deviation. And I'm asking you the probability that a sample has some characteristic. Guys, I know, let's dial in here, right? I know stuff about the population, and I'm asking you the question that a sample will have, what's the probability a sample will be a particular way? What are you more likely to have access to, a sample or the whole population? A sample, right? So what you want to know is, hey, I found this sample of 30 individuals. It has a mean of 100. Like, what's the probability that the mean of the whole population is above 105 if this mean that I have is 100, right? Something like that. I would want to use the population to make inferences about the whole population, right? Does everyone follow what I'm saying here? I, right now, have information about a population. I'm using it to figure something out about a sample. That's like backwards of what you would actually imagine would happen in reality. Getting some blank looks. Does that make sense? Because why would you have information about an entire population? And if you did, why would you really care about a sample? You have the more important piece of information. So this is kind of what you do, right? So you identify significant results with probabilities by using the rare event rule, right? So you use some assumptions to find the particular probability of an event. And if you see something that happens, right? And based on the assumptions that you went in with it, the probability of what you just saw happen was 1 in a million. There are two possibilities, right? The probability really was 1 in a million, and something very rare occurred, right? Every so often, very rare events do occur. More likely is that your assumptions that caused you to calculate that probability were wrong. Is everyone kind of following? This is what we will do in chapter 8. And we will do that, and I'll kind of give you an example with this one, right? So let's take out some information, right? So it is widely believed, right, based on previous research, this is common knowledge, right? That the mean body temperature of human beings is 98.6 degrees Fahrenheit. And that the standard deviation is 0.062 degrees Fahrenheit. My pen has been damaged, or the tip, which is why it's writing so poorly. Maybe these will write a little bit better. All right. And so so everybody, I'm going to actually have you work on this example, so you should pay attention right now. N is 106. Now, let's say you do an experiment, right? And you randomly select 106 individuals, and you find that the mean of that sample or no, we'll do it this way. So what it's asking is, I want to know that, so I take 106 individuals, right? What's the probability that their mean is, not this, right? I have 106. My mean is just a little bit lower than the accepted value. Let's find out the probability that this would happen by chance, right? So is this a individual or is this a sample? Sample. So you need to use the formula z equals, and do I divide by the standard deviation or by something else? I never said that. That's the variance equal to the variance though. But what's the change that I have to make? You can easily see it here. Huh? Speak up. The standard deviate, but what standard deviation? It's right in front of you guys. So do I divide by the standard deviation of the population? What? 189 was the mean, but it was 39, but for the idea that had a sample, did I use the standard deviation of 39? What did I divide by instead of 39? What did I use instead of the standard deviation of the population? I used the standard deviation of the sampling distribution, which I calculated by taking my initial standard deviation, right, and dividing it by the square root of n. Does this sound familiar? That's what you're going to need to do here. I'll give you that, right? But then you need to do the rest of this on your own. I'm going to come around and help you, all right? So have everything that you need, and well, we should have done assumptions. I don't know if it's N is 106, so it doesn't matter, right, if the body temperatures are normally distributed or not, because my sample size is over 30. So this is totally okay to do. All right, everyone try to do this. I will spend some, like, maybe the last 10 minutes. This is taking much longer than I thought it would, right? But we did get some time to work at the beginning, right? So to do this. So try this, right? You've been paying attention. You just follow the same procedure we did before. You have all the numbers you need to calculate. I'm going to turn on some light. We seem a little sleepy. Feel free to move around the room, talk to people, right? Talking, communicating is a good part of learning. I did about half the work for you, right? I wrote down the numbers. I wrote down the formulas. And I would start here because I'm going to need that for my z-score. This is just plug and chug. I gave you the formulas. That was the hard part.
What would the X bar, the, you know, one closest to the,
What do you mean the X bar? What's the formula?
well, no, what would the X bar be? Because I'm looking at that one. I'm trying to think that it'd be 98.3 then, right?
98.2. I don't know where you got 3. That's not.
Because it'd be greater than, oh, no, never mind.
Yeah, just use 98.2. Don't need it. Yeah. So, because we're saying what's the probability that the mean is greater than this? Remember, like temperature is a continuous distribution. So you don't really need to worry about that, right? Because 98, yeah, you can treat it less than and less than or equal to are basically the same thing, right? The probability that for a continuous distribution, the probability that you choose exactly any value is basically 0. So let's start here. Let's start by writing the information down, right? Yeah. So sigma of X bar, so sigma means standard deviation, right? Right. Standard deviation of X bar, that's standard deviation of the sampling means, right? That you calculate by taking the standard deviation of the population and dividing it by the square root of n. Hope you know how to use the square root on your calculator. I think you've done it before. So let's see, X. So the standard deviation of the population, 62 is 0.62. I'll start this out. You do this, you will get approximately close enough to 0.060. Now you have everything that you need for this formula. You can easily find a z value. You can just kind of see the steps. For step one, look at, right, identify the important quantities. See if it's a situation where you're looking at an individual or a sample, right? In this case, it's a sample. If it's a sample, calculate the standard deviation of the sample means, and then use that to calculate a z-score. Once you have a z-score, sketch it out, and then either find the answer using the table or your calculator. Like that. This is X bar, so that's the mean. This is the standard deviation here. Notice how you used it twice, so that number should be this, because that is the sample. Yeah.
What's X?
It is X bar. So X bar is the mean. We want to find out the probability that our mean is 98.2 or lower. So that would be the 98.2. It is the information about the sample. You have a z-score yet? You got that number. So that's what's going to go in the bottom of this formula. Now get you your z-score. So z-score, I'll write this out. Your z-score will be, so your x mean or your x is always going to be equal to like the information that's about the particular sample, or if it's not a sample story of one about an individual, that. So we're saying, okay, what's the probability that a sample has a mean of 92.6 or less? So to know that, I have to know how different is 98.2 from 98.6. So to do that, I subtract and I divide by the standard deviation, but the standard deviation is the standard deviation of samples size 106, not, you know. Anyone calculate this? Yeah. Now, Stux, you just asked, you know, maybe a younger sibling, is 6 or 7 a big number? They might say no, but as far as standard deviation, 6 or 7, is that a lot of standard deviations? Yeah, so it's to the left, right? So notice we want to find the probability that our mean is less than this. That's going to, since we converted that to a z-score, we're trying to find this area right here. And again, if we look at our table, what do we find? We find this number 6.6? No, right? But even if we just go to 4, right, 3.99, our area is 0.00003. So I can say that this yellow area right here is essentially, guys, 0. So this probability approximately 0%. Now they calculated exactly, they actually got 0.0001. So it's really a little more than that. It is 0.01%. So let's use, this is what we'll be doing 2 chapters from now. So hopefully you guys can calculate this. Let's think about what this means. So let's say, so you are a biologist or you research human body temperature. I don't know why, right? Okay. You look, the literature says, right, the mean human body temperature is 98.6. The standard deviation of the body temperature is 0.62. You collect a size of 106 people. You find that their mean is a little less, or it seems like a little less, 98.2. But you do this calculation, and we found out, so this is why, like I was telling you guys, right? We're going to eventually reverse this. So under the assumptions of common knowledge, a sample like ours that would have a body temperature as low as this sample that we just collected would be 1 in 10,000. Would be the probability that we get at that low of a body temperature or lower. So there are kind of 2 possibilities. One possibility is just we just happen by chance, because remember, our people are randomly selected to choose like the 106 coldest people in Illinois. That doesn't seem that likely, right? What is the more likely thing that happened? No. Let's assume that the temperature, that's done correctly. So we got this probability by using what assumption? Well, we calculate it using this mean and this standard deviation. And we are told this is the population mean. And this is the population standard deviation. Something very unlikely, if those things are true, something very unlikely just happens. So what's more likely is that our underlying assumption is false. So this study suggests that that mean and that standard deviation, one or both of them, are wrong. Think about it, right? If I flip a coin 30 times in a row it comes up heads each time. What is that? Just use your intuition. What does that tell you about the coin? It's rigged, right? So the hypothesis that the probability of getting heads is 50% is probably false, because with that assumption, what I just saw happen in front of me has a very, very small chance of occurring. Everyone following? Right? If you see something that has a very small chance of occurring, right? Based on assumptions, right? We are told somehow, we're just using this population mean and standard deviation because some authority told us this, right? It's unlikely that someone actually, or it didn't happen, let's just say, no one measured everyone's body temperature. So let's just see here, right? Let's just see how they say it. I want you to think about this, right? I want you to talk about this each other, right? Our result shows that if the mean of our body temperature really is the published value, the value published by the University of Maryland, right? The probability of getting a mean, right, a sample mean of 98.2 or lower is very, very, very low, right? It's basically 1 in 10,000. So that means there are two possibilities, right? The population mean really is this, and this sample just happens to be very unrepresentative, even though it was randomly selected, right? Something that has a 1 in 10,000 chance of occurring could occur, right? Right? Just like if I flip that coin in front of you and you get 30 heads in a row, that has a non-zero chance of happening, right? So when you see that, you would say, either I just witnessed the rarest event of all time, or the assumptions that I used to calculate that probability are incorrect. So, right, this is what you would actually know. You would actually have a sample, right? So this is what we do in chapter 9. This is why we have to know this, right? So like this section, right, the whole central limit theory section is kind of like we're God. As God, we know what the actual mean is. We know the population mean. We know the population standard deviation, right? God communicates that to you. You can then calculate what's the probability that a sample size of 106 will have a mean lower than a particular value. You don't actually have that. So this is what we do, right? You do a test. If the results of your test are very unlikely to occur, right? Using the assumptions are probably false. How unlikely to occur, that is a question that you have to kind of answer for yourself, and we'll talk about that later. But this is just the test here, right? Notice that you're not quite following this interpretation. That's okay. I won't assess you on that, right? What I need you to be able to do is to get this 0%, right? We will do that later. Questions here? All right, I'm going to assign a homework on this, right? So here's, I think what's going to happen, because I am worried. I want to get a better score than I did last semester. So this is what I've decided to postpone the test. I think I'll postpone it by a week. So what we're going to do, right, on Wednesday is I will, at the beginning of the class, give you a project, right? It will help you see the effects of the central limit theorem, right? I will start out that project. It will be done on Microsoft Excel, right? This is why I told you to do that Excel assignment months ago. Some of you did not. You're going to really struggle, but hopefully you'll figure it out. So bring your laptop. I will help introduce this project to you, and then you will have the rest of the time to either work on the project, work on the practice celebration, work on the homework, right? So please bring something to work on, right? Ideally, you'll bring your laptop. Otherwise, you'll have to do it on your own. It's easier to follow along with what I'm doing than to just do it on your own. Does everyone understand? Okay, so I'm going to end class. It's a little early. Maybe you can use this time to check in on some of the practice celebration, right? Read over it. The answer key is up here, right? And also, I'm not going anywhere immediately after class, right? Please, make sure you're learning. What? Yeah, it's up there. I will also, you don't need to photocopy each page because I will also post it to Canvas right on the top. Okay.